Hello, this is the Datashreks team represented by Omar Ansari, Felipe Lopez, Richard Levine, and Sky Sheffield. And our project for the Big Data for Healthcare Fall 2020 course was replication of the MGP-TCN algorithm for early sepsis detection using AWS technologies for faster data processing and feature extraction. So let's first talk about sepsis in the United States. Sepsis affects 1.5 million people annually. It is a very costly medical condition, and a significant number of deaths happen annually in this country. And needless to say, it is an unsolved problem, and it is an area of great interest for the medical research community. As far as the definition goes, sepsis is a life-threatening condition characterized by infection and organ failure. Two definitions exist in the industry. The one on the left is more qualitative, looks for 2 out of the 4 conditions to be met, where the more latest definition, which is sepsis 3, is on the right, which essentially has a qualitative part, which is 2 out of 3 conditions have to be met, and a quantitative part, which is a SOFA score, or a sequential organ failure assessment score, to detect the onset with a delta of 2. And the score is actually calculated using biomarkers, which are available from records of patients coming to ICU. And the patients are monitored continuously, and the data is extracted. When those biomarkers cross certain thresholds, the SOFA score increments. And it is seen that ICU mortality increases with higher SOFA scores. And let's talk about why early detection is critical. Death happens within 3 days of onset of sepsis, and each hour of delay can add as much as 8% decrease in survival rate. And it can go as far as 7 hours of early detection can increase 28% survival rate. Machine learning for early detection for sepsis has had much research done in the industry. Weibull-Cox, recurrent neural networks, LSTMs, all have been utilized for reasonable success. Our direction was to use MGP-TCN, which was multitask Gaussian process, which is the first step to takes data which is irregular and interpolates that, makes it regular and sequential, and then feeds it into the second part, which is temporal convolutional networks, TCN. And this is a form of convolutional networks which is able to create deep learning models for time series classifications. And the output of all of this is obviously the sepsis labels. A little bit more details. The input and output have to have the same length. We use zero padding to ensure the size is maintained. And the convolutions are causal, which means the past informs the future. So the window that you select in the past to capture the dynamics essentially inform how the prediction happens in the future. Our objective for this project was to replicate early sepsis detection in a model that was proposed by the Moore team, the Moore et al. Team, which is basically quoted at the bottom. They use traditional relational database technologies, the Postgres database, and we noticed that when we tried to replicate that, pre-processing was extremely slow. It took about 13 plus hours on the laptop as far as SOFA calculation, feature extraction goes. So our goal essentially was to speed up this processing by using cloud-based big data technologies. And the intention behind this, the motivation behind this, was that if we can contribute this back to academia, then people can build on this research, do it faster, and accelerate progress. So double click on the approach within AWS. Essentially, we took the data from Mimic, which was the MIT data source, into AWS. We took it into 3 areas: the S3 bucket, the AWS Glue service, as well as the SageMaker service. Now, mind you, the SageMaker service, as you can see in the middle, was used largely for just some little pre-processing, data cleaning, and exclusion parts. These parts actually happen quite fast in the traditional model as well within Postgres. So this is not really the area of focus for us in terms of speed up. The area really we focused in as far as the software engineering aspects was the glue portion, the middle purple box, which was doing the actual analysis and the loops that we had to run for the convolutional network. And this was based on Scala, which is on Spark, and we tried multiple different variables for the environment. The output was fed into AWS S3 in a bucket. And these CSV files were then taken back into a local setup where we did a little bit more post-processing and then the actual model was actually run on the laptop for training and testing. So what were the results? Well, the results were very fruitful. While the traditional model performed better in the beginning, all the way to the 52nd epoch, we noticed that it started to really have drastic spikes after that. But the Spark Glue model that we had that was running on Spark Glue processing that we had running on AWS was consistent all along the way. As a consequence, the Spark Glue processing was 20% faster than the Postgres-based processing. So this project was essentially a success. We noticed that the summary statistics that came out of this processing were kosher. So all the important statistics were correct. The case control patient numbers, the distribution of gender, admission types. We just made sure that the output that we had coming out of our Scala Spark-based AWS processing was like-to-like, apples to apples, and was consistent with how the actual traditional processing looked like. And the answer was an affirmative. The deep learning part, essentially we used the performance was measured by AUC and AUPRC. AUPRC is area under precision recall curve, and the idea over here was to protect sensitivity in an imbalanced data set. It was very crucial to be accurate about being positive, because this is in fact sepsis, right? And sepsis causes death. So that's why AUPRC was an important method to measure the performance. We did try some improvements like dropout for regularization. We tried deeper TCN windows so we can see if there's deeper patterns in the past which would change the model for the future predictions. We also tried some adaptive learning rates. Essentially, these didn't have major gains in improvement. However, the scores were still within the bounds, and the scores that came out were AUC of 0.82 and AUPRC of 0.38. So in conclusion, we can safely state that our project was successful in replicating on Spark in the cloud technologies. We did increase the speed of the processing. We did hit the right performance metrics and targets. And we did, in fact, use Spark RDD and transformations and actions as we had promised in the proposal. Some future work that we do recommend is improving MGP-TCN and the memory management that is required, as well as this model essentially is more of like an academic model, since you have to run the model again every time for new predictions. So this is not production ready, and for that we feel that more of a TensorFlow aspects introduced in the MGP side will actually enable us to persist this model and in fact improve the memory management aspects as well. Thank you very much.